So we have Ernest Rutherford, who is one of the Regents' favorites. And in terms of atomic history, he's a very important scientist. Here he is. He was not from England. He was from New Zealand. And he disproved his professor, his teacher, Thomson's plum pudding model of the atom. So to remind ourselves, we had the hard indivisible sphere, the lax lacrosse ball. That was Democritus. And John Dalton also believed that. Then we have J.J. Thomson, where you've got the positive sphere, and then you've got the negative charges evenly distributed, kind of like the chocolate chip cookie, or as he called it, the plum pudding model. So now we're going to go on to Ernest Rutherford's model of the atom coming next. So through his experiment, it was called the gold foil experiment. That's how he came up with his model of the atom. So going in, he knew that there were something called alpha particles. These are kind of envision it as like a laser beam. So we're going to talk later on about how certain things, and maybe you already know, certain things decay, radioactively decay. And when they decay, they emit particles and energy. And so alpha particles are the beams given off by decaying radioisotopes. And there's a whole bunch of those on reference table N. Some of them give off alpha, some of them give off beta, and other ones. So he was using an alpha decay material, and he knew that they were giving off this positive beam of the particles. And so if he was shooting that or aiming that beam, which again, you cannot see with the naked eye, but you can observe the repercussions of that. You were going to shoot it at a piece of metal. He chose foil that was made out of gold, so not aluminum foil, but gold foil. And he chose it because it's very, very thin. If you think of like a gold leaf you put on dessert, it would pass easily through, maybe a little bit of deflection. So his experiment was just that. We were going to bombard, which means like attack, a very thin sheet of gold foil with a narrow beam of alpha particles, and watch what happens. So here we have his experiment. You've got your thin piece of gold foil here in the center, this blue that goes around. That would be where you would be able to detect the presence of the the alpha particle, and you'd see like a little flash. Over here to the right, we have the lead box, and the alpha particle emitter is some kind of a radioisotope. So we'll talk a lot more about that word later. It's some substance that is unstable as it is, and so it's going to be giving off radiation in the form of this beam of alpha. So take a look at what's going on. So the beam is coming through. Looks like most of the beam, see how it's this very thick line? Most of it goes straight through, which is what you would expect from a very thin piece of gold foil. However, some of them go through, but then they like veer off. And very, very few of them come directly back to the source. He was not expecting that. So imagine you had a piece of newspaper and you shot, oh my gosh, not an artist. You shot a gun and you expect that the bullet's going to go straight through, but instead, pa-chow, hits you instead. That is not what you would expect. So there's got to be something that caused the alpha particles to bounce back. So again, let's talk about his findings. So here he is actually with his apparatus for the gold foil, which I cannot tell you what all that stuff is. First of all, because it's an old picture, but second of all, also, I don't know. So like we were showing here, the majority of the particles did go straight through. Some of them bounced off at very, very, very large angles, and some, I'm going to say, instead of some, we're just going to say very few bounced straight back to the source. What would make it come back to the source? Now, let's unpack this for a second. alpha particles are positively charged. So earlier we discussed how similar charges will repel or try to push away from each other. So if you have positives being repelled, that would indicate the presence of something positive within the atom. So something very, very small, because most of the beam went straight through. So there's not a lot of these small positive things. Maybe you've already guessed it because you know about it. There were two conclusions. The first conclusion is because the atom is allowing most of those beams to go straight through, it's composed of mostly empty space. This is such a very strange concept for students to understand, because we think of these hard indivisible spheres, we think of solids with atoms packed tightly together, just like billiard balls or lacrosse balls, but instead we have all this empty space. It would be like if you had an apple and then a kilometer away, you would have your first outer electrons. Which, again, electrons, where would those would be what J.J. Thomson discovered. So, wow, this is really, really big. Again, to scale. When we're talking about the atom, obviously atoms are not kilometers wide. They are very, very small, so we would have to scale it down. But to the scale, there is a ton of empty space. But this center, this is positively charged. We know that it's positively charged because the positive alpha particles deflected or repelled. And when other ones came close, they kind of skirted away. That's why some of them bounced off at large angles. And so all the mass and all the charge inside the atom is in the center, and it's called the nucleus of the atom. So according to Rutherford, his atomic model is called the nuclear atom, where we have things called protons and neutrons. So let me clarify. He did not come up with the idea of protons and neutrons until later, once he experimented more. And neutrons, he worked with James Chadwick. You ever heard of Jimmy Neutron? Jimmy Neutron is named after James Chadwick, who was the co-discoverer of the neutron. The more you know. So protons and neutrons making up the nucleus came later. But for right now, he just knows that the center of an atom is positively charged. It is very, very dense. It is in the center. And we've got these negative electrons around it. So we are throwing plum pudding into the garbage can. And we are saying hello to what we call the nuclear atom. So here we have the nucleus. And then you would have empty space until we have the electrons. Now, this is not a great representation. This is more artistic rather than scientific. So you would have your positive nucleus, and then you'd have electrons way the heck out here. And even that's not truly to scale either. So that's Ernest Rutherford, which was a really important and groundbreaking atomic model. We still believe a lot from what he came up with. And so this is why the Regents really focuses on his experiment and the conclusion. So of all of our atomic scientists, his is one of the most important breakthroughs. All right. Thanks for watching.